Hello, welcome to the NPTEL online certification course on deep learning. We have started our discussion on the neural network, and in our previous class we have talked about the basic implementation of few of the logic functions, the AND, OR and XOR function using the neural networks. Today we will continue our discussion with the neural network, and particularly we will talk about the feed forward neural network, also known as multi-layer perceptron, and then we will see that how these neural networks can be trained to solve certain problems. So, for that the algorithm that we will talk about is what is known as back propagation learning algorithm. And in fact, we will talk about back propagation learning in details. The reason being that this back propagation learning is the basic of the deep learning or the deep neural networks that we are going to discuss in future. So, just to recapitulate, what we did in the previous class is that we have implemented three of the logic functions: AND function, OR function and XOR function using the neural network, and we have seen that in case of an AND function, if the input is x1 and x2, for unified representation, as we have done before, that we have appended an additional component which is equal to 1, and this is what helps in giving a bias to the neural network or every nodes in the neural network. And the weights that we considered was minus 1.5, 1 and 1, and with this we have seen in the previous class that output becomes x1 and x2, and that is what our AND function. In case of an OR function, of course, there was a nonlinearity involved in it. The nonlinearity that we have considered was a threshold nonlinearity. That means, if the output or weighted sum of the input, that is W transpose X, this was greater than or equal to 0, we have assumed the output to be 1, and if it is less than 0, we have assumed the output to be 0. And with that, we have seen that this network, this simple node, implements an AND function. Similarly, in case of OR function, again our input is the binary input x1 and x2. The bias term in this case is minus 0.5. Here we have given the weights as 1 and 1, and with this again we have seen that the output becomes x1 or x2. We could implement this AND function and OR function using a single neural network, because we have seen before that these functions are actually linear functions. I can separate the outputs which are 1s from the outputs which are 0s by a straight line, which is not possible in case of an XOR gate. So, XOR is a nonlinear function, and we have seen in the previous class that because XOR is a nonlinear function, so it cannot be implemented a single neural network or single neuron. So, I need multi-layer neural network, and that is what is in this figure. So, here again our inputs are 1, x1 and x2, those are the binary inputs, and one of these two gates we have seen before that it implements an OR gate, and the other one implements a NAND function. So, let us assume that the first one implements an OR function and this one implements a NAND function. So, for implementing OR function, just as we have seen over here, our weights will be minus 0.5, 1 and 1, and for implementing a NAND function, it has to be just complement of AND. So, weights for implementing NAND function will be plus 1.5, minus 1 and minus 1. and these two outputs are finally to be ANDed, because our XOR function x1 XOR x2 is nothing but x1 or x2 ANDed with x1 NAND x2. So, here I have to have an AND function. So, for this weights will be minus 1.5, 1 and 1. So, here at the output what I get is x1 XOR x2. So, you find that these are simple implementations of the logic functions using neural networks. Now, from particularly this XOR function, it is quite obvious that if the function that you have to implement or the problem is a nonlinear problem, the nonlinear problem cannot be solved using a single layer network. I need multiple or multi-layer neural network for implementing a nonlinear problem. So, for a nonlinear problem, as we also have seen in the previous class, that I have layers of neural networks. So, I have neural networks in multiple layers, and from every layer, say layer 1 to layer 2, I have complete connection, that is every node in the layer 1 is connected to every node in the layer 2. And if the final function, so here you find that there are k number of layers. So, at the output I call the output layer to be kth layer. So, the final function that is being implemented is fk, okay, and the input layer implements a function f1. So, with my input vector as x, the first layer, that is f1 layer, it implements function f1 of x. The second layer implements f2 of f1x. Third layer will implement f3 of f2 of f1x, and finally, the kth layer implements fk of the output that has been generated by all the previous layers. So, when it is a nonlinear problem, we can say that all the layers from f1 to fk minus 1, they will implement a nonlinear mapping, because as we said earlier that if I have a nonlinear problem, then instead of trying to design a nonlinear classifier, you try to map the input vectors using a nonlinear mapping function, so that they are mapped into intermediate feature space, and in the intermediate feature space, this nonlinearly mapped input vectors will be linearly separable. And then finally, at the final layer or at the kth layer, I can have a linear classifier to classify all those samples correctly. So, all these layers from f1 to fk, they actually implement this nonlinear mapping. So, at the output of fk, the new feature vectors that I get, so feature vectors x, which are now linearly separable, and the kth layer I can implement a linear classifier which will classify all these vectors h which are now linearly separable. So, this is just a block diagram representation of a multi-layer perceptron or a feed-forward neural network. Now, why it is feed-forward? Because I am inputting the feature vector x at the input layer, they are being processed at every layer and being forwarded in the forward direction to the next layer, and finally, you get the output from the final layer at the output layer, and nowhere in this path the information is fed back to the previous layer. So, always the information flows in the forward direction. So, it is feed forward network. But we will see later that for learning or for training this neural network, the error is propagated in the backward direction, because our aim is to minimize the error by adjusting the weights in between the layers. So, for training this neural network, the error is propagated in the backward direction through each of the layers, and while it is being propagated, at every layer the weights are updated in order to minimize the error. So that is why the learning algorithm is known as back propagation learning. So our neural network is a feed forward neural network, but the learning algorithm is a back propagation learning algorithm. Now let us see in details that how this neural network or multi-layer perceptron that looks like. So this is what is a somewhat detailed representation of this feed forward neural network. So here I have assumed that there are k number of layers in the network. At the beginning, we have an input layer which is represented as 0th layer. The purpose of this layer is simply whatever comes at the input is simply passes to the output. So this layer does not have any other function other than simply passing the input to the output. And every other layer from 1 to say layer k minus 1, each of these layers participate in nonlinearly mapping the input feature vector x to a new feature space h. And kth layer, which is represented by capital K, it is the final output layer, right? And we also assume that from every layer, every intermediate layer k, where this k is represented by lowercase letter, the nodes are connected or the neurons are connected to the next layer, which is k plus 1. And this connection is complete in the sense that every node in the kth layer is connected to every node in the k plus first layer. And if I take an ith node in the kth layer, it is connected to jth node in the k plus first layer through, so let me put it like this. So I take a node I or a neuron I in the kth layer, and I take a neuron j in the k plus first layer, which is the next layer. So the output from the node I is connected to the input of node j. Output from node I in kth layer is connected to the input of k plus first layer through a connection weight, which is w I j k plus 1. So this is the convention that we will use when we discuss about the back propagation learning. So this is the overall architecture of our feed forward neural network. There are k number of layers. Kth layer is the final output layer. Every node or every neuron I in an intermediate layer k represented by lowercase k is connected to the next connected to the jth node in the k plus first layer through an weight which is given by w I j k plus 1. And the purpose of training this neural network or learning is that iteratively using the training vectors, you try to find out what should be the value of w I j k plus 1 for every I, j and k, so that the neural network is finally trained to solve your problem. So that is the purpose of back propagation neural network. And in this network, you find that as we are feeding the input xi, so for training, the training data is fed in the form of xi, yi as a doublet for say I is equal to 1 to n, where n is the number of training samples I have, which is given for training this neural network. So for every training sample xi, as it is labeled because these are used for the training purpose, I know that to which class this sample xi belongs. So xi in this case belongs to class yi. So if I have a binary classification problem, we will do that quickly. This yi can be either 0 or 1. If yi is 0, that means the sample xi belongs to say class omega 1, and if yi is 1, that means the sample xi belongs to class omega 2. So this tells you that what is the class belongingness of the training sample that I have. If I have C number of classes, then yi will take one of the values 1 to C. So, this yi in that case is the index to the class to which xi belongs. So, if I have a data xi 5, this is the training data given, then this means that the training data xi belongs to class 5. Secondly, at the output node, if I take a jth node, jth neuron at the output layer, I represent the output of the jth node in the kth layer as xjk. So, these are the conventions that we will use when we talk about backpropagation learning. And here you find that only at the output given a training vector xi, only I know that what should be the corresponding output, because if it is xi2, this is the training pair that is given, I know that when this xi is fed to the input, output of the second node that should be high. The outputs of all other nodes should be equal to 0, because my training pair says that this vector xi belongs to class 2. Similarly, if a training vector x is given which belongs to class 9, then when I feed this x to the input, only the output of the 9th node from the output layer should be high and all other outputs should be low. So, this I can decide only at the output layer. I really do not know that what should be outputs of any of the hidden layers, that is not visible. So, that is the reason that all the nodes or all the layers except the output layer, they are known as hidden layers, because I can only observe, I can only decide at the output, I cannot decide what should be the outputs of any node in the intermediate layers or hidden layers. And this is a layer, as we said, that this is known as input layer. So, the purpose of every neuron in the input layer is simply to pass whatever is coming to the input to its output, and it is subsequently fed to the neurons of the next layer. So, this is what the architecture of the neural network looks like and the conventions that will follow. Now, let us see that how can we train the neural network, or what is backpropagation learning. So, to talk about backpropagation learning, first I will consider a very simple neural network consisting of a single layer, which is the output layer. Of course, you remember that we said before that using a single layer, I can solve only linear problems, I cannot solve any nonlinear problem. And as I said that this learning algorithms will do in details, because this forms the basis of all subsequent deep learning or deep networks, deep neural networks that we will talk about. So, it is very important that you understand the backpropagation learning very, very clearly, right. So, again I take a single network, a single neuron, where the weight vector is w. If I feed an input vector xi, so as we said before that for training I get the input vectors as pairs xi, yi, where this yi is the class index to which this vector xi belongs. And as we said that this is used only for training purpose. During actual testing or when you deploy such neural networks, I have an unknown vector x, I do not know what is the y. If I know, then I do not have to classify that, and that classification will be done by the neural network only. So, here as I have, or as I feed such an input vector xi, I expect that the output of the neural network should be yi, and only when I get the output as yi, which matches with my true values, then at least this xi is correctly classified by this neuron. But what we get is, I get a value xi hat, which is an approximation of xi. So, if xi hat, so this xi hat is nothing but w transpose xi, where w is my weight vector and xi is the input vector. And for the time being, I am assuming that I have a neural network with single layer and single output node, and I am not assuming there is any nonlinearity in this neuron. Okay. So, my output simply becomes w transpose xi, and I am assuming that this w transpose xi is an approximation to yi, which is yi hat. So, if yi and yi hat they are same, that means my input vector is correctly classified. So, I do not have to take any action to modify the weight vector w. Now, suppose yi hat and yi they are not same, they are different. Okay. So, my error will be y hat minus yi, this is the error, and what I compute is the sum of squared error. So, this is sum of yi minus xi, where this I will vary from 0 to n. So, this squared error is computed over all the training vectors that I have as I varying from 0 to capital N, and I have capital N number of vectors for training purpose. And I scaled this by half. The reason of scaling it by half is, as we have seen earlier also, for any learning algorithm or any training algorithm, we go for gradient descent approach. That means I have to take differentiation of the error function or the loss function that we have generated. And because it is squared error or squared loss, so having a factor half will simplify our expressions. So, that is the reason this half is put. If I put it in an elaborated form, so this error function or the loss function E is nothing but half of w transpose xi. This w transpose xi is nothing but our y hat. So, w transpose xi minus yi square, take the summation over all I varying from I equal to 1 to n. That means you are summing the errors of all the training vectors that you have. Next, as we said that we will employ the gradient descent approach as we have done before for training the network or for updating the weight vector w. So, I take the gradient of E with respect to weight vector w, and here you find that this gradient is nothing but y hat minus yi into xi, where xi is the input training vector, right. And now you find that why we have put this half, because otherwise there would have been a scaling function 2 over here, scaling factor 2 over here. So, in order to avoid that, you put half. So, this is the gradient of the error or the loss, right. So, I have to update w or the weight vector in such a way that this loss is minimized or the error is minimized. And for that, as before, my weight updation rule follows the gradient descent procedure. So, my weight updation rule will be simply w gets, if this is the previous value of the weight vector, the updated weight vector will be w minus some eta times the gradient. What is this eta? We also said before that this is nothing but a rate of convergence factor. So, this eta indicates if the value of eta is very high, then the rate of convergence will be fast. If the value of eta is low, then the rate of convergence will be low. So, I will have a slower convergence. Of course, both has their individual merits and demerits. We also discussed about those before. Now, if you look at this weight updation rule, you find that we get something more. I said my output y should be either 0 or plus 1. So, if it is 0, it belongs to one class. If it is plus 1, it belongs to another class. And if you remember that earlier the linear discriminators that we have talked about, that is a linear plane which separates two different classes which are linearly separable. We have said for one of them If W transpose X greater than 0, then it belongs to one class. If it is less than 0, it belongs to another class. Now, here let us come to a situation that if I find that W transpose X is greater than 0 for samples belonging to some class omega 1, and this is represented by yi is equal to plus 1. So, as long as my W transpose xi is greater than 0, then it is correctly classified, right. Now, here you find that if my yi is plus 1, but I get yi hat to be negative, then, and instead of taking the sum, let us consider a single feature vector xi. So, which is nothing but stochastic optimization. We have also talked about that before. If you sum all of them, that means you are considering all the training vectors together, it becomes a batch optimization technique. So, we have talked about batch optimization, mini batch optimization and stochastic optimization. So, if I consider only xi, that becomes a stochastic optimization procedure, and then our weight updation rule will be simply W gets W minus eta times yi hat minus yi times xi. So, here if my yi is actually plus 1, that means W transpose x should be greater than 0 for correct classification of xi. But suppose W transpose x, which is nothing but yi hat, happens to be negative. In that case, this yi hat minus yi, this whole term will be negative. And in effect, what we are doing is we are making W, updating W as W plus some factor, say eta times, let us put chi times xi. So, here you find that there is some similarity with the Perceptron algorithm that we talked about towards the beginning of our course, that if an xi is misclassified, we add a fraction of xi to the weight vector for weight vector updation, right. In the same manner, if I assume that yi is 0, for which this yi hat should be negative because it belongs to the other class. But if I get yi to be positive, yi hat to be positive, so over here my yi is 0, that means xi belongs to another class for which yi hat, which is computed by this neuron, should be negative. But if I get this as positive, okay, again as before, the updation that I am doing is W as W minus some eta chi times xi. So, this is the other vector for which W transpose xi should have been negative, but it has been misclassified because yi hat has been positive, has been computed as positive by the neuron, by the neural network. And in this case, what we are doing is we are subtracting a fraction of yi from W, or in the other words, we are adding a fraction of negated yi to W. Again, the same thing that we have done in case of our Perceptron algorithm. So, this is what you have in case of single layer perceptron, that following gradient descent procedure, the way we update the weights or the weight vector is by adding or subtracting a fraction of the misclassified samples to the weight vectors. So, I will stop this lecture here. We will continue with this next. Thank you.